Hello, I'm John Kerr. I'm the Director of Sales and Technology for Andritz out of Glens Falls, New York. Our company supplies process equipment for the pulp and paper industry. What I'm going to address to you today is about the pulping of recovered fibers. First, I'd like to cover what types of pulpers there are. In order to settle on the terminology, we've included this list, which includes continuous pulping, batch pulping, high consistency pulping, and low consistency pulping. And between those four parameters, we can pretty much encompass all the technology in recycled fiber repulping. Continuous pulpers are characterized by the charging, the pulping, and the discharging or the dumping of the pulper all done on a continuous basis, that is, at a constant mass flow rate. Whereas batch pulping is done so that the pulp is charged into the vat or into the receiver, into the pulper, and then completely defibered or run to a certain period of time or for a certain period of time until the fiber is completely distributed throughout the slurry so that it's a consistent mass. High consistency pulping is by definition done at consistencies which are typically in the 11, 12, to up to 18% range. Medium consistency pulping might be done in that 8 to 10 range. Low consistency pulping, conversely, is done in the 3 to 4% range. This would typically be for a low consistency continuous pulper applied to, say, an OCC plant or a plant that's making linerboard using old corrugated containers. Whereas a batch pulper, a high consistency batch pulper, might be used for a de-inking plant where we're repulping in order to add chemicals, add steam, get the chemistry right, and then do a batch cook, essentially, of the recycled fiber. So once we decide whether we've got a batch or a continuous process, then there are also two different types of continuous pulpers, either a vat type or a drum type, and we'll go through those in just a moment. In terms of the operating consistencies, we recovered that. And then the rotors that are used are slightly different between the three. There is an attrition rotor, which is used in a low consistency pulper. Attrition meaning that there is fiber to fiber action with interaction with the metal. That is, the rotor itself is impacting the fibers. There is a pumping impeller used in medium consistency or mid consistency pulping, which actually draws the fiber down into the attrition rotor. And then there's the helical rotor, which is used in a high consistency batch pulper, and that promotes the circulation that causes the hydraulic shear or the rubbing of the fibers together, so in order to promote the removal of inks and the distribution of the debris, or the removal of the debris from the fibers themselves. In terms of processes, typically mechanical pulp furnishes are used for mechanical type grades, paper grades. The product, for instance, might be newsprint, in which case you would use news, magazine, those types of furnishes. For chemical pulp furnishes, that is ledger and book stock, we're going to make printing and writing grades or perhaps tissue grades, maybe even market pulp. And then for unbleached furnishes, these would be typical for linerboard, corrugating medium, packaging grades of all kinds, sack kraft, things like that. There's another grade of paper which is mixed waste, which is a lower cost furnish, which is typically used for some other types of packaging grades. Extended fiber sources might consist of recycled core stock. These would be the cores from tissue toweling operations or from carpet mills, things like this, where we can recover the fiber cores that form the basis of this roll stock that we would recover that material from. Wet strength, beer carton stock, chicken boxes, produce boxes, that sort of thing, where there's a lot of wet strength that's required to be added to the fiber in order to give it its mechanical properties as it goes in and out of its storage cycle, in and out of coolers and whatnot. A lot of wet strength is added to that, and that requires a specific kind of repulping chemistry in particular, temperature, and a particular pulper type. Highly coated waxed boxes, and these are again the produce boxes, the meat boxes, which make up a fairly significant sector of our industry, where we need to learn how to recover this material. Very good fiber, but it's contaminated with high quantities of wax coatings, which we have to do something with. The wax is intolerable in the paper making process. Then we have curbside collected waste, which is generally a residential mixed paper, commingled with everything that you might find in a garbage heap. And we need to learn how to design systems to separate out that material. And so repulpers are required to certainly accommodate that kind of material. And then municipal solid waste, which is truly garbage. This is when we have to do some very gross size separation of the materials in order to separate the cellulosic material that we want to have in the recycled fiber stream. All this requires specific pulping design changes that we can accommodate through the existing technology, but with some design changes. When we talk about contaminant removal, we'll talk about some specific devices. The ragger, for instance. The ragger is used in a low consistency continuous pulper tub where consistencies are in the 3 to 4% range. And the ragger is basically just a rope that is thrown into the tub, allowed to drag into the solution so that the vortex action inside the pulper will wind the stringy material up on the rope itself so that it can be removed on a continuous basis. There's a junk box or a junk tower, and these receivers are collection points, low points in the system where heavy material can collect and can be removed by the use of a grapple hoist. And I'll show you some diagrams of that in a moment. The Pulper Screen, or the Detrashing screen, is a common device to both high consistency batch pulpers and low consistency continuous pulpers. This is a device that basically is a secondary pulper which is used to isolate the contaminants, further deflake the stock, that is to recover the fiber bundles, and to segregate the heavy and the light contaminants from one another for separate recovery or disposal. Then the trommel screen is a rotating drum screen which is used to recover or separate the fiber that's freed up from the rejects, put that back into the process, ultimately separating out the plastic material. So what's the function of a pulper? There are 3 basic actions inside any pulper, regardless of the type. Its first function, of course, is to wet out the fiber so that we can pump it further on into the process. We can't handle high solids material, so we have to reduce the consistency down to something where we can move it through hydraulic pumps. The paper making process is, of course, aqueous, and so we want to have the water solution such that we can pump it trouble-free. So the first thing a pulper has to do is to wet the fiber out. Next, we have to get good circulation. The good circulation will promote the separation of the fibers from their individual bundles, as well as to allow the material to fall out that is non-paper making fiber. The plastics will float, the heavies will sink, the styrofoam will come out, the PET bottles, the cassette tapes, that sort of thing. So all that is promoted by recirculation or circulation inside the tub. And then, of course, attrition, which is the fiber to metal action inside the pulper itself, which is really what tears the fiber flakes apart and allows the individual fibers to come free from the matrix of the dried paper. So the function of the pulper is quite different. We want to now make sure that we can prepare the stock for subsequent treatment in the system. All the following unit operations have to handle the pulp as it's prepared in the pulper. We want complete defibering in the case of batch pulpers, or partial defibering plus deflaking in the case of continuous low consistency pulpers. We want to have good contaminant removal. If we can do more good contaminant removal in the pulping loop, then we'll have less problem later on in the system with contaminant removal and having debris in the final pulp quality going to the paper machine. And in the case of de-ink pulp, we have a chemical reaction that's taking place. We'll dose the proper chemistry into the pulper for the de-ink plant so that the ink can be removed from the fibers in the pulper, maybe some bleach added, maybe some stabilizing chemicals, so that the flotation cells and the washing system can act to its highest efficiency. So the objective of the pulping module should be to achieve the maximum defibering possible. If we can leave the pulper with as few flakes remaining in the pulp as possible, then we will have better fiber recovery and better system yield, which yields, of course, much better economic advantages in the operation of the system. We want to have maximum contaminant removal. This seems rather obvious, but we want to do as much contaminant removal in the pulping loop as we can, because that's where the debris is generally the largest. So if we can remove the debris to the best efficiency in the pulping loop, then we'll have a better overall system debris removal efficiency. Of course, we want to do that without applying a lot of work onto the contaminants themselves, thus maintaining their size and their integrity. The impeller, the drive, and the tub design all have to work together to optimize energy consumption so that we don't consume too much horsepower in repulping the stock and getting it prepared so that it can be properly treated on down with the rest of the system. The materials of construction that we choose to build the pulper out of must withstand the abrasive environment and the extensive abuse that happens in this end of the system. So it must be extremely rugged and suitable for paper mill duty, which means that we have to do a lot of sophisticated engineering analysis on the structure of the pulper itself, making sure that it doesn't vibrate, making sure that it has enough capacity to withstand the constant loading and unloading and the horsepower that's applied to it. The mechanical equipment must be easily maintained. That means that we have to design in the concept stage of the machinery development, we have to design the system so that it can be easily maintained in the environment in which it's used. And then, of course, when considering the process of the de-inking pulper in particular, we want to achieve appropriate fiber swelling so that we get the right ink detachment. That is, for printing and writing grades, where we dose the chemistry into the batch pulper itself, then we have to provide adequate mixing, we have to provide adequate volume, and we have to design the pulper so that that pulping module achieves those objectives. Here is an illustration of a typical low consistency pulper. You'll see that the rotor itself is in the bottom of the vat. There is an enclosed top, which is really an option on it. This one happens to have a doghouse on the top where the pulp bales are fed through. So figure number 1 there is where the pulp bales are fed. They'll come in and drop directly in on top of the rotor, which is in the bottom of the tub. The rotor is driven by a gearbox and a motor, and the pulp then, as it's circulated around inside the tub, will be extracted on a continuous basis through the extraction chamber, which is below the rotor. There can be some recycle streams that come back from the process. Typically these are coarse reject loops, things like that, that would come back into the pulper, which is signified by item 4 there. And then the consistency control water, or maybe some additional pH adjustment. Some chemistry could be added through nozzles that are indicated there on position 3. But the basic concept is that there's a constant flow of water coming into the pulper itself, along with a constant flow of fiber, so that the consistency is maintained about 3 to 4%, and we continually extract pulp from the pulper at that point. This is a cutaway of the bottom of the pulper tub using what we call a 3-piece rotor. It's a 3-piece rotor because, oddly enough, it has 3 pieces. There is a hub, which is attached to the drive shaft. There is a rotor cap. And then there is the vane ring. The vane ring is indicated in red on this diagram. And over here in the exploded view, you can see this is the vane ring. This is where the attrition happens. As the fiber is introduced into the tub, then the rotor is turning, and the fiber will be trapped underneath the rotor as the rotor passes by, and the flakes are then rendered apart by the mechanical action of the rotor itself. So as the rotor passes over the holes in the extraction plate, these provide the cutting surfaces by which the mechanical energy can be put into the flakes so that the slurry is defibered appropriately. As it gets to the point where it's small enough to fit through the extraction holes, then it is pulled down into the extraction chamber, indicated by these areas underneath the rotor. And so this is basically a donut-shaped annulus where the pulp is collected and removed from the pulper. The pulper drive can be either a gearbox, as shown here, or oftentimes a belt and sheave arrangement. It just simply depends on the capacity and the size of the pulper and the nature of what we're trying to do. These are many different types of rotors, or there are many different types of rotors that are available to be used in tub-type pulpers. What's referred to as the tornado rotor here is specifically used for wet strength, where there's a lot of fiber integrity in the structure itself, in the dried paper. Chemicals have been added in order to give it its strength, even though the fiber matrix gets wet. And so we need a lot of mechanical action to tear that fiber matrix apart. And that's provided by these sawtooth arrangements on the stator and the rotor tips as they come in close proximity to those. And so that will physically tear the paper apart. A very high attrition, very aggressive rotor. Does an excellent job on beer carton stock and ice cream stock, things like that, where we need a lot of mechanical energy to pull it apart. This slush maker rotor is basically a rotor that's used for virgin fiber repulping. So if we've got virgin bales, it comes apart very easily between the attrition teeth on the outside of this rotor and the rotor itself, which has the deflecting vanes here. So that pulper would not do too well in a recycled environment because of all the places where the plastics and the heavy material could hang up, but it does extremely well for virgin fiber stocks. The Delta rotor, on the other hand, has attrition bars underneath the extraction plate. And the extraction plate, it has actually attrition bars with radially drilled holes, and it has extra vanes welded to the top of the rotor. And that rotor might be used most effectively for OCC or DLK, which would be packaging grade furnaces. Very difficult furnaces to pulp apart or to tear apart, requires a lot more horsepower and a lot more attrition than, for instance, a de-inking stock or a newsprint furnace. This mid-con rotor is a hybrid. This is used at a consistency of about 8%. It basically consists of a turbine which has been attached to the top of a low consistency rotor. The pulper would be operated on a batch basis at about 8 to 11% consistency. The turbine is there to pull the stock down and increase rotation or circulation inside the tub so that the attrition can happen at the low consistency rotor, which is mounted on the bottom. Pulper tubs themselves are in fact different. We rarely now see a round tub for circulation anymore. What happens is that if we still have a round tub, then there will be internal baffles that are inserted so that the pulp doesn't simply sit inside the round container and circulate around. What we want is good turnover, good circulation. We want the pulp that's on the top of the tank to come down to the bottom and see the face of the rotor, to be subjected to that attrition energy. Another way to accomplish that is to use a tank that's not round, as found in the double sigma or in the D-tank arrangements. The concept here is to move the vortex from the center of the tank off to one side so that we increase the submergence by forming a hydraulic nip that actually pulls the paper down into the rotor. And so we get this rotor interface, this attrition energy, which rends the fiber matrix apart more effectively. Low consistency pulper detrashing can be done in a number of different ways. This illustration shows a fairly standard arrangement where the pulper tub itself receives the bales of pulp or paper, and it's continually filled with water. The consistency there is 3 to 4%. About 80% of the capacity of the pulper is removed underneath the rotor through the main evacuation point. That is, the accepts of the pulper come out underneath the rotor, and about 80% of that comes right directly to the suction of the dump pump. The balance of it will flow out through some sort of a pant leg arrangement here so that it goes to a large tower. And this tower is typically 4-foot diameter, and it is at the same height as the existing pulper. So that there is an overflow box here, which is a gravity feed overflow box which controls the level in both the pulper and in the junk tower. What happens is when the stock flows out of the pulper here, the heavyweight contaminants, the metals and whatnot, will collect in the bottom of the tower and of course can't float up to the top of the surface. The styrofoam, the plastics, the oversized debris that is lighter will all float up and come over the weir box and go down into the pulper detrashing screen. So the metals that are left behind can then be removed by a grapple hoist system, which is lowered down periodically into the bottom of the junk tower, and the material can be removed. This is typically the operating floor level about here, so that there is a dumpster or some sort of dump cart which is available on the operating floor for it to receive the heavy contaminants, which can then be removed from the mill or sold to a scrap dealer. That keeps the trash out of the basement and makes cleanup and housekeeping much, much easier. The Pulper detrashing screen itself, its function is to separate the heavy and light contaminants from the pulp slurry. And if successful, about 20 to 30% of the total capacity of the pulping loop will be produced just by the Pulper screen. So if you've got an existing pulper tub that is limited in capacity, that is not being currently detrashed on a continuous basis, then this is a good option for increasing tonnage. The concept of the Pulper screen itself is such that we want to isolate the flakes from the balance of the pulp slurry to do some additional work by attrition in the Pulper screen to remove the fiber on a continuous basis and then reject any remaining material that's left behind on the pulper plate, or the screen plate in the Pulper screen. The light material will be periodically purged up to the drum screen where the fibers can be recovered. That is the trommel screen that we talked about earlier. And then the heavy material is simply discharged periodically back to the bottom of the junk tower where it can be removed by the grapple hoist. Here's a diagram of the high consistency batch pulper. This again is a batch process. We add about 30 to 40% of the total volume of water into the pulper before we add the pulp. The rotor would be going at a fairly slow speed in order to provide the mixing necessary. We'll put the pulp bales into the pulper and allow it to slurry, and then add the balance of the water, increasing the rotor speed so that we get the proper circulation. Again, consistency in the tub is going to be in the 12 to 15, 18% range. This is a very, very viscous slurry, so it takes a lot of energy. It takes a lot of acumen of the pulper design itself in order to get the pulp to circulate around and actually be defibered. What we're looking for in a high consistency batch pulper is fiber to fiber action, that is hydraulic shear. This is what removes the ink and the debris from the fibers themselves. We'll run the batch process until the fibers are completely dispersed. So typically we'll take a grab sample out of the pulper and look at the deflaking index, that is the dispersion index, to make sure that all the fibers are dispersed as well as we can make them before we'll dump the process. So it is a batch fill, batch pulp, batch dump. Here is a diagram of the batch process. It still incorporates the high consistency batch pulper, which has some opportunities for metal and heavy contaminant removal in this device before it flows on to the Pulper screen. Now you'll notice that 100% of the production of the pulper loop comes through the Pulper screen. Because there is no under rotor extraction in the high consistency pulper, 100% of the stock will flow out of the side of the tub, through the Pulper screen, through the screen plate at that point, and then into the dump tower. The material that is retained on the plate is then purged to the drum screen where fiber is recovered and returned to the pulping cycle, and then the plastics can be rejected. So for design principles of high consistency batch pulping, we'll set the pulping time, which is equivalent to that time that's required to get complete defibering, or defibering to the degree that the mill requires. The design basis again is circulation. We want to make sure that the rotor and the tub work together in order to circulate the pulp to get that fiber to fiber friction that's required in order to do the ink dispersion and the ink removal, get the fiber swelling that we're looking for, really preparing that pulp for the subsequent unit operations. We want good equal circulation and good velocity profiles throughout the cross section of the tub in order to make sure that we have as homogeneous a slurry as possible going throughout the tub, so to increase our ink removal efficiency. This is a diagram, or actually a photograph of a typical pulper rotor for a high consistency batch pulper. Almost all turbines are three-bladed in their design. But you'll notice the terminus of each of these blades, that they are swept out in such a manner that the pulp is pushed up the sides of the pulper tub so that it turns back in on itself. So the pulping circulation is such that it goes down towards the rotor on the inside of the vortex and then is up on the outside of the pulper tubs themselves, assisted by the baffles that are in the tub as indicated in this photograph here. You can see the baffles around the outside of it. There are different types of high consistency pulper turbines, and this particular photograph shows cast turbines. And the reason that we would make a cast rotor instead of a fabricated rotor is that this is a heavy duty application that are receiving impacts, multiple impacts from the bales being dropped into the pulper. So we want to make sure that it's robust and suitable for paper mill duty. Here's the circulation pattern in a high consistency pulper tub. Again, you see the action of the baffles, the diagram illustrating that what we're looking for is a circulation pattern that has come, the rotor is pulling the stock down towards the bottom of the tub, and then the rotor vanes are pushing the stock up the walls. And because pulp is thixotropic, that is, the harder you push on it, the harder it is to push. It simply does not respond. It's a non-Newtonian fluid. It's a very difficult thing to pulp fiber in a high consistency batch pulper. So that's why all the particular attention is taken to designing the rotor, designing the tub to work in concert so that we get this all-important circulation in the high consistency batch pulper. This is a Pulper Screen, a typical diagram which shows a nice exploded view. This is what's called a rotor bed plate type device, because we have a bed plate here, which is a drilled pattern extraction plate through which the pulp has to travel, the accept pulp has to travel. It is cleared by a rotor, which is driven by typically a belt and sheave arrangement. But this rotor circulates over the top of the bed plate and acts to defiber the stock. It's really a secondary pulper. It has the same relative action as a pulper rotor, with the exception that what we're trying to do now is to clear a screen plate and really do some additional defibering to make sure that there are no flakes remaining in the accept pulp. Another common feature of almost all pulper detrashers or pulper screens is some sort of heavy contaminant removal. So in this particular model, this is the entranceway for the pulp. So it would come down, heavies would continue to sit down here in the bottom or be removed on a double valve junk chamber, which would be attached out here. The pulp then circulates around by the action of the rotor. The accepts would go through the screen plate and report here. Then the light rejects would periodically be purged out of this nozzle here so that they can be taken up to the trommel screen. As we said before, sometimes these pulper screens are pressurized, sometimes they're atmospheric. It just simply depends on the make and the model and the style and the vintage, but they all do basically the same job, and that is to continuously remove the debris from the pulper tub, which avoids the problem of having to shut down the pulper, pull the stuff out of the tub, and start the batch over again, or start the process over again. So for our detrashing system, really the benefits are that we get increased pulper uptime. That is, that we don't have to shut the pulper down periodically to drag the material out of it that is accumulated. In the recycled fiber, there's going to be contaminants. They're going to end up in the pulper. And a rule of thumb is that if you have over 5% debris in your pulp stream coming to it, then you should have some sort of a continuous detrashing device connected to it, or some sort of strategy or system, mechanical system attached to the pulper tub. We want to remove those contaminants before they're broken down, again, to improve the overall system removal efficiency of the system. We want to have improved fiber recovery. That is, we don't want any fiber losses from the pulping loop portion of it. In the old days, we would say that we'd get about a 1, maybe 1.5% shrink from just the mass coming into the pulper versus the mass leaving. Now it's closer to 10%, but none of it's fiber. It's because of the debris loading in the pulper itself has gone up because of the commingled nature of secondary fiber. We want to have, excuse me, an accept that feeds forward on a continuous basis in order to give us increased capacity of the pulper loop. This is again the accept from the Pulper detrashing screen, which then can go right directly to the Pulper dump pump. There are some styles which are used still, which have a Pulper detrasher which is attached, a module that's attached right directly to the pulper, and it simply recirculates right back to the pulper and does not take stock downstream to the Pulper dump tank. So it doesn't add any capacity per se. What it does is simply remove trash on a reasonable basis in order to keep the pulper uptime. So it gets capacity by increasing uptime, not by producing stock of acceptable quality. Here are the Detrasher rotors that are fairly typical. We spoke recently of the module that is added onto the side of the pulper tub and does internal recirculation around the pulper tub only without accepting downstream. That's what's known as a scavenger design, or a scavenger type. And this rotor works by centrifugal action, so that the pulp is thrown across this slot. You can see you can see a blow up here of the slot, this annulus that is all the way around the circumference of this rotor. And so as the pulp is thrown across the annulus, then the fiber makes it through this small slot, whereas the trash does not. So the plastics and metals and whatnot would be thrown and retained in the Pulper detrashing screen itself. And then as the fiber is extracted on a batch basis, the scavenger is then pressurized with air. The pulp is pushed back into the pulper, leaving only the contaminants behind, which are then discharged into the basement or the pulper pit. The multi-blade rotor type pulper detrasher, this would be used on a de-ink stock or a soft furnish, where we've got swept back blades and an extraction plate that covers the entire back of the pulper detrashing screen. And this type of detrasher will act on a consistent basis during the pulper discharge. So for a high consistency pulper, we'll drop the consistency down about 3 to 4% and feed it through that pulper detrashing screen, and that blade will continually keep that extraction plate open so that we can extract the entire pulper charge in one setting. The last illustration would be the shearing rotor, and this kind of rotor has flat rotor face surfaces, very aggressive, intended to do some additional defibering of, for instance, an OCC stock or a packaging grade furnish, where we need to put an additional horsepower into the flakes, the wet strength flakes, or the remaining flakes that are coming from a low consistency continuous pulper. And there's one more design which is kind of unique, and that is for poly-coated or wet strength furnishes, where we want to use a particular chemistry in the high consistency pulper, where we can add the right chemistry to get good defibering, and then we need to separate those fibers from the high levels of contamination that are in the pulper. Bacon board, the meat packaging, that sort of thing, which has 30% polycoat to a very good substrate of SBS fiber, or solid bleached sulfate fiber. It's a nice bleached white fiber that we want to recover and use in our paper grades. Very available. All the printing is done on the plastic coating, and so if we can separate the plastic coating from the fiber, then what we're left with is, of course, a very valuable fiber. But the difficulty is that it's such a high percentage of plastic. And so this system will enable us to separate those two components very effectively. We can do complete defibering in the high consistency pulper. Then you have, for instance, out of 100 tons of polycoat, you'll have 70 tons of fiber, 30 tons of plastic. We'll put it across this trommel screen by just dumping it right through the screen, and the plastics will come out the end. The fibers will be accepted to the screen, and we've made our separation. So it's a very, very unique but successful method by which we can separate highly contaminated furnishes from their fiber substrate. This is a typical flow sheet for a high consistency pulper detrashing system, where once we finish the batch of pulp, that it's completely defibered to the degree that we desire. Then we open a valve that removes the pulp from the tub and dumps it through the pulper detrashing screen. And again, we'll want to extract this entire tub volume through that pulper screen. We're pulping at 18% consistency, so we have to add some dilution water into the top of the tub in order to drop the consistency to something much more reasonable, say 8%, and then we'll add trim water to get it down even further to say 3 to 4% consistency that it can go through the pulper detrashing screen. Then the accept pulp goes to the dump tank with the material that's retained on the screen is either heavy or light. The light material can be purged up to the buffer tank and then onto the trommel screen with the addition of some dilution water to cut the consistency there to about 1.5%. The recovered fibers from the trommel screen can go right back into the suction of the pulper detrashing screen, in effect adding that fiber back into the slurry. Any heavy material then is retained in the fiber detrashing screen and is purged periodically to some sort of method where we can haul it out of the mill or again sell it to the junk dealers. Why is it important to do early decontamination of the total system? And this graphic here will show you the reason is. We want to get that debris out in its largest form possible as quickly as we can get it out in order to impact the overall efficiency of the system. If you'll notice that if this line, I apologize for not having numbers on here, it might make it a little easier to discuss, but if we start with the same input and we do a better job of detrashing in the pulper, then we come into the coarse screening loop or the subsequent unit operation with a much lower level of debris if we do good pulper detrashing. If we don't, then we have a higher level of debris coming into coarse screening, which means that out of the coarse screens, we're going to have a higher debris level. Now you'll notice that the slope of this line is steeper than the slope of this line, which means that with higher incoming debris, that our efficiency of removal is better on a percentage basis. But that doesn't really matter to us. What really matters is the level of debris we have coming out of the coarse screening loop, going to the fine screening loop, and subsequently on out throughout the system. So even if you have a very simple system, removing debris early on will give us a better result out of the system in the end. Let's move on to talking about drum pulpers. We've talked a lot about tub pulpers and batch pulpers and continuous pulpers. Now we're going to talk about drum pulpers. Now these devices are very different design. They look entirely different from tub pulpers. These are basically long tubes where the pulp is continuously put into one end and extracted out of the other. It's a continuous high consistency pulper. And these pulpers operate at about 15 to 18% consistency depending on the pulp type. And then the stock is diluted in the screening zone, which is in the tail end of the pulper, to about 4 to 5%. If you look at the diagram, I'll show you. This is the chute by which we add the pulper bales, or the pulp bales. They need to be broken apart and dewired first, so no wires are allowed in the drum pulper. So the individual sheets of paper, that is the boxes or the newsprint or whatever it is, it has to be loose paper that comes into the chute. And it comes into the pulping section, and you can see the lifters here on the inside of the shell of the drum. The same is true for the different types of drums that there are from the different suppliers or vendors that make these devices. But in this particular case, there are two separate drums that accomplish the pulping and the screening. In this case, there is one constant drum that controls the pulping, and then this is the screening section. And in this one, this is the pulping and then the screening section. But you can see the lifters here. So as the drum turns, it lifts and drops the paper over and over and over again until it's finally defibered. And then it's finally put into the screening section here, which has a drilled screen plate instead of a solid steel drum. And it has dilution water that's added in the end, so that this pulping consistency here might be 15–18%. It drops over into the screening zone where the consistency is dropped down to 4–4.5% into the vat and pumped away. It has a single drive on it with typically a girth gear around which then rotates the drum pulper much like a lime kiln. It goes at about the same speed. It's a very slow device. Its intent is to simply lift and drop the pulp until it disintegrates because of the impact of the wet pulp against the steel parts of the drum. This technology has been extremely popular. This is rather old data, but you can see that the trend continues to this day. This is for mills in Europe and Asia and the Pacific Rim, but you can see where new capacity has far outpaced the HC batch pulper with the drum. So for de-inking in particular, for old news, for magazine furnishes where we're making lightweight coated grades or we're making newsprint grades, de-inking grades, certainly the drum pulper technology has taken over in terms of processing technology because of the improvements that it offers for the system efficiency. Here's a graphic that describes the lifting and dropping I was talking about earlier, where we turn the drum just fast enough to make sure that the pulp that falls across the longest chord of the diameter of the pulper. And we'll change the diameter of the pulper in order to achieve different capacities. There are other technologies which use the same diameter of the drum and just make it longer, give it more residence time. But in any case, what you're looking for is a net energy impact of the pulp lifting and dropping a number of times in order to get complete defibering, so that there is no impact on the contaminants, but rather only on the fibers. You can imagine what would happen to a piece of plastic. If we put it in the end of the pulper, it's going to be lift and drop and lift and drop and lift and drop, but it's not going to have any net impact on the plastic parts itself. So the contaminants will come out essentially in whole pieces, whereas the pulp fibers, of course, will be stripped away. So this is excellent technology for like aseptic packaging, where there's a foil and plastic laminated together with good usable fiber. We can separate that very, very effectively in a drum pulper type of environment. Old newsprint, magazines, these sorts of things. The spines on the back of magazines used to be the bane of paper makers because that would produce a lot of stickies for the de-inking plant, whereas the drum pulper now can strip away the fiber and leave the magazine backs intact, essentially. Here's a control system for the drum pulper. Very simple, actually. We've unbaled the paper. We've put it across some sort of a bale breaker or a waterfall type device to make sure that it's loose paper. We have a metering device to make sure that we control the amount of the volume that's on the weigh scale. We use a nuclear scale in order to measure the mass of the paper coming into the pulper, and then we'll adjust the water flows both into the pulping section and into the screening zone according to that mass weight that we record on the nuclear scale coming into the pulper. So that essentially the production point is fixed by the weigh scale. There is a mill that is unfortunately currently shut down in Sheldon, Texas, which rebuilt their line they had 2 high consistency batch pulpers feeding their system, and they replaced it with one single drum pulper when they did a capacity expansion. And that enabled them to completely revamp their system and simplify it dramatically, eliminating coarse slot screens and eliminating their cleaners. Some of their reverse cleaners in particular. Because the drum pulper does such a much better job at stickage removal, then we can eliminate reverse cleaners out of the design of the system, which makes it overall much lower capacity, or much lower capital cost and much lower operating cost because we've eliminated these unit operations. Here's a photograph of that actual installation. It's an 1,800 ton a day pulper, 4¼ meters in diameter, 35 meters long. Quite a large pulper. Actually, it's the largest drum pulper in the world. But again, a very, very successful installation, but unfortunately Abitibi Consolidated elected to shut down that entire mill. Not because of the pulper, by the way. Here's a typical feed system where you see the bales are broken apart and it's the loose paper that is fed up the conveyor. What you don't see in that picture is the waterfall that actually fluffs the paper up, and then there is a leveling conveyor which makes sure that the volume is constant on the sides of the conveyor itself, so that when the paper hits the weigh scale, that it has a constant volume to measure. And here's a photograph of the feedstock. When you're using aseptic packaging in particular, or heavily poly-coated or foil-coated papers, the poly-coat and the foil will all be removed essentially intact Very little work done on those contaminants, whereas the pulp is, of course, separated out from the substrates and freed up in order to be used again. And this will give you an indication of the difficulty of furnishing and what might lead us to applying a drum pulper versus a tub pulper. These are some lab results with a drum pulper, and you can see that the OCC components require a lot longer pulping cycle, a lot longer pulping time, and may not be as good a candidates for drum pulping technology as, for instance, for the newsprint or the lightweight coated material. So this is a nice handy chart to have. We look at the different pulper types, batch or continuous, high, medium, or low consistency, what the applications might be used for, and then the detrashing equipment that might be associated with each one. And you can see that continuous high consistency pulpers, that is the drum pulper, requires very little detrashing equipment because it has its integral trommel screen, whereas the balance of the tub pulpers have somewhat more elaborate but no less effective detrashing strategies which are deployed for those applications as well. Some other pulping technologies that are coming on stream. Steam explosion has been played with for quite some time. This is where we'll charge wet paper into a steaming tube and release it to atmosphere over a blow valve, the action of which will rend the paper apart into its individual fiber components. Not used commercially yet, but certainly of interest to the technical world. That continues to be studied year after year. Biochemical pulping, that is enzyme pulping, is an emerging technology and something which we find very interesting, but again finds limited commercial use at this point. The autoclave technology, on the other hand, is a sanitizing method by which we can mine landfills. We can actually go out and dredge up the remains or the contents of a landfill, separate out the box springs and the mattresses and the tennis shoes and all the associated non-paper making components, and separate those out with screens, separate out the metals with eddy current separators, and really the residual that's left over that's coming from the autoclave can then be sent into more or less a conventional fiber recovery strategy, which allows us to recover very, very good usable fiber that can be used in corrugated medium or in some cases linerboard. So autoclave technology is being commercialized as we speak and should be up and running very, very shortly and be a viable commercial technology. Thanks for your attention.